6.6 on binomial situations. So if you're given a percentage, then most likely it's going to be a binomial situation. So we would have P, which would be that percentage, Q, 1 minus P, and N is the number of attempts or trials or sample size. You may remember we also did the binomial formula, and there was also the fact that if N times P is bigger than 5 and N times Q is bigger than 5, the binomial situation, which is actually discrete information, can be approximated with a bell-shaped curve. The bell-shaped curve is usually for continuous situations. Anyway, all of this seems like review. So what's new in this section? Can't we just keep doing the binomial formula forever? It was pretty fun. Well, what if n equals 1,000,000? And you need to find the probability that x is bigger than 700,000. So then, are you kidding me? We would have to do binomial formula 300,000 times? There's got to be a better way. Well, there is. We need to go over something before we get to actually solving problems. So for a continuous random variable, so when x is something like age or volume as in three-dimensional space, like how much volume a cup can hold, not volume how loud the radio is. Anyway, when you've got measurements like that, then if you had, for example, you're supposed to find the probability that x is bigger than or equal to 4, you would just draw a bar at 4, shade to the right, and then do the z-score and look that up in table A2. But for discrete random variables, the story is different. So discrete means it's taking on countable values, like how many shoes a person owns. 1, 2, 3, 4, etc. So take a look at this. Over here, here's the possibilities. They don't own any shoes, or there's 1, 2, 3, 4, 5, or 6 shoes. So for this fourth shoe, what's the probability a person owns exactly 4 shoes? Since there is a discrete probability for that, so let's say it's 10%, then this red area would be 10%, or 0.10. Since this is a rectangle, a bar, it has to have a left side and a right side. Well, here's the possibility of owning 3 shoes, and here's the possibility of owning 4 shoes. So there has to be a dividing line between those, and that's what this 3.5 is. Likewise over here, here's owning 4 shoes, here's owning 5 shoes. There's got to be a bar dividing those two. It's at 4.5. So those decimals, 3.5 and 4.5, are called continuity corrections. In other words, the bell-shaped curve is continuous. The bars, which are found by doing the binomial formula, those are discrete, and we need a correction so that we can, when there is a bell-shaped curve for these bars, which this is not a great example, it doesn't fit that great, but when they fit very well, then we need this continuity correction of 3.5 or 4.5. You then have to decide, should I use 3.5 or should I use 4.5? With this case, it said x is bigger than or equal to 4. So that means we are supposed to include this bar right here and then shade to the right. So we would actually be going from 3.5 to the right, and this is what's meant by using the continuity correction. You do the regular z-score, but you would use the 3.5. Okay, now on to an example. The chances of winning blackjack, 44%. Suppose that a person played 200 hands of blackjack. Wow, they had a lot of time to waste. No judgment here, though. What's the probability they win at least 90 of those hands? So here's the mathematical information that we need to set up, the P, Q, N, and what we're supposed to find. At least means bigger than or equal to 90. So we have this mean equals N times P. Calculate the standard deviation. And here's what the picture would look like. So you put mean of 88 right in the middle of the graph. Then next would be 89, 90, and 91, because we're counting how many hands of blackjack that they won. So it's going to be a whole number, 88, 89, 90, 91, etc. So for this 90th win, so this is when the person wins exactly 90 times, there you could do the binomial formula and find out this red shaded area, but it would have to go from 89.5 on this side to 90.5 on this side. So in this case, which one should we use, 89.5 or 90.5? It's going to be the 89.5 because when it says at least 90, we need to include the 90. So you have to start just a little bit to the left of it and then shade all the way to the right. And that way we will include this bar for the 90th win at blackjack. Then we do the regular Z formula. We find out Z equals 0.21. Then just look that up over here. 0.21 would be this of 5832. Now because that's the left side of the graph, we would then have to subtract from 1 to get the right side of the graph. So there is a 41.7% chance of winning at least 90. Let's try one more. According to what I just Googled, the high school graduation rate in Salinas, 64.5%. So there are, I believe, 4 public high schools in Salinas. So it's saying when you look at all 4 of them together, 64.5% graduation rate. Now suppose there were 1,200 freshmen out of those high schools, chosen at random. Find the probability fewer than 750 go on to graduate. So again, write down the numbers that we need for our 2 little formulas, n times p. And the standard deviation is the square root of n times p times q, so that's 16.576. And then for the picture. So here is the 750th person to graduate. So this is if 750 out of the 1,200. And then for this person, their bar would start out 749.5 on the left and 750.5 on the right. So which of those 2 red numbers do we use as we shade? So this says shade to the left, and we're not supposed to include, because it said fewer, we're not supposed to include the 750. So that means we're going to start at 749.5 and then shade to the left. So then pop out the Z formula. It tells us it's a negative 1.48. Look at the negative Z scores. 1.48 would be right here. And this table gives us the left tail, so that's just going to be the answer right there, 0.0694.